Okay. I move here and
see.
And please also double check the audio because I haven't done it.
Yeah, I'll check as soon as it starts.
Thanks.
Have you started?
I should have started the recording. Yes.
See. All right, I see something. Okay, it's all working.
Nice. Nice.
All right. Bart, are you ready?
Yes, yeah, I am.
All right. So I think maybe we just get started with it. So thanks so much for joining us, both Bart and Thomas. So we're gonna hear about the recent paper from Mechanistic to Compositional Interpretability. So yeah, please go ahead and take it away. Thank you.
Okay, yeah, thank you for having us. So maybe just to introduce ourselves, yeah, my name is Wart. I'm a PhD researcher at the University of Brussels. And Thomas?
Yeah, I'm Thomas. I am a researcher at GoodFire on the life sciences team applying interpretability to scientific discovery on biology models.
All right. Okay, so the slides are shared, I presume. Thank you for having us. In this talk, we are going to do a bit of what I like to call armchair interpretability. We are not going to look at individual models, but we want to answer one simple question. What does it mean to make a neural network interpretable? How could we formalize that? And how can we measure it? We will do this in 3 parts. First, I'll give a short introduction to the existing interpretability paradigms and the gaps between them. Then Thomas and I will try to bridge those gaps within our framework of compositional interpretability. And then finally, Thomas will make it more concrete, give some examples to show that we also actually try to practice what we preach. So, neural networks can solve complex problems, but not because we designed them to solve those problems. We designed them to efficiently learn to solve them by building their own internal representations. Take this model, for example, it detects pneumonia, and it may get it right most of the time, but we don't actually know why. So to use it safely, we need to know how those representations are actually being used and when they fail. Also, the adoption of AI systems now requires regulation. And currently, regulation is starting to ask questions that even the designers of those systems cannot answer themselves. So as a result, interpretability as a science has needed to evolve. We started out by asking very specific questions, like what information was used to make this particular decision? You can answer this just by looking at inputs and outputs. Those types of explanations are behaviorally faithful. They correlate with the input-output behavior of the system. But they are also quite limited because we don't really know how that information was used or how the next decision will be made. We can sidestep all of those problems by using models that explain all of their behavior by construction, often using logic or probabilities. This gives us strong guarantees because the explanation is simply the structure of the model itself. But we pay for that by constraining the architecture. So recently, mechanistic interpretability is trying to study how a model can solve not just one instance, but a general class of problems. This requires us now to also understand the internal representations and essentially reverse engineer them into parts that we can understand. And the goal is now explanatory faithfulness. We don't just want to reproduce what the model did, but also how it did so. So this new approach essentially explores the terrain in between post hoc and intrinsic interpretability. But without formal foundations, it can be a bit like looking for a needle in a haystack, without actually knowing what a needle looks like. You always tend to find something. So these methods, they work often heuristically, and we don't really have a good way to evaluate or compare the explanations that they offer. Okay, so how should we operate in this muddy middle? This is why we propose compositional interpretability, a formal framework to study how we can make those mechanistic methods faithful, simple, and consistent. And we want to do this in a way that is objectively measurable, so that it can be tested and automated. We do this based on two principles. The first one is compositionality. The meaning of the whole should follow from the meaning of the parts and how they interact. If we understand the parts, we should be able to explain the whole model, and also vice versa. The second principle is Occam's razor. All else being equal, we should prefer the more concise explanation. And for this, we will use minimum description length. Taken together, they let us cast interpretability as a constraint optimization problem. Now, note, both principles are agnostic to the model itself. So you can think of this as a mathematical template that you fill in to evaluate and improve the quality of explanations. And for today, we are mainly going to focus on the actual intuitions rather than the specific formalizations. Okay, so what is a compositional interpretation? At its core, any interpretation is just a map from a system's behavior to an explanation. It translates the semantics, C, of that system, for example, the functions or distributions that are being implemented, into some human interpretable explanation E. That can be natural language, pseudocode, concepts, a causal model. It doesn't really matter. We don't want to make any assumptions about the explanation E, so that this is the one object in our blueprint that can remain subjective, dependent on the goals and the specific knowledge of the interpreter. So, for example, we can look at this box M, look at the inputs and outputs, and label it as an orange cat detector. But this is post hoc. It doesn't tell us how those cats are being detected. So let's try to open up this box and now associate the semantics with a particular structure, a syntax S. This lets us decompose our model, M, into building blocks at a certain level of abstraction. And this syntax is pure wiring. It is like essentially organizing your Python or PyTorch codes into modules. The result is a diagram that says what components exist and how the information flows between them, but not actually what the components compute. A compositional model is then just a mapping from syntax to semantics, assigning to each box the functions that it implements. And we call this mapping the representation of our model. Now, models usually already come with a representation. Think, for example, of neurons, layers, attention heads, etc. So a compositional interpretation now can have a double grounding. It should still depend on the semantics of the model, but it also has to respect the actual syntax of the computation. And those two paths, they should agree, they should commute. If we interpret the local components step by step and we put them together, it should be the same as interpreting the global behavior. This essentially eliminates two failure modes. If we only ground in semantics, then the explanation becomes causally disconnected from the actual mechanisms. Two different implementations of the same function might very well map onto the same explanation. Second, if we only ground in syntax, then we are just labeling components without actually checking what they do. Okay, so I have been waving my hands quite a bit so far. So I just added this slide to assure all of you that this can indeed be formalized using category theory, which is like the mathematical language of composition. On the left, you can see the definitions of compositional models and interpretations. And on the right, you see a formalization of those string diagrams that I have been using. These can essentially be interpreted in different semantic categories. For example, we can use Cartesian spaces for neural networks, stochastic maps for probabilistic models, and so on. So, the advantage of doing all of this work is that we now get a formal bird's-eye view of the field. We have one language in which we can systematically compare interpretability techniques and the assumptions that they make. We could go even further. We could, for example, also consider input-dependent syntax, like a mixture of experts model, or we can try to decompose the weight space so that we can give meaning to individual parameters, and so on. But okay, how can we actually use this? Well, if we follow this line of reasoning, the goal of interpretability is to associate each AI system with a compositional interpretation that is as complete as possible, meaning that every component in this syntax gets some explanation. And that may sound very strict, but Tull et al. Have actually shown that any model that we consider to be intrinsically interpretable automatically satisfies this requirement. For example, a decision tree, each node in that tree is a question about a question about a feature, and the tree structure tells us how those answers should combine to make a decision. So compositional interpretations are a proper mathematical generalization of intrinsic interpretability, and we should try to work towards them. But compositionality is only really a structural constraint. It defines for us the space of all the valid explanations, but it doesn't really tell us what explanations are good and which ones are bad.
And so to give some intuition on this, I think it's useful to step back to just looking at normal algorithms. And I've taken as an example likely the most ubiquitous set of algorithms, which is just fastest path algorithms. So here there are two algorithms which to find the fastest path, which is first brute force, just computation O factorial of n, something like this, or Dijkstra, which is likely one of the best well-known algorithms, which computes the fastest path in like O n log n time. So it's a very elegant method to find more efficient algorithms. And the thing is here, the results that these algorithms produce are the same, and like very intuitively it makes sense. Like we need some kind of selection criterion where we can classify like, oh, we just want to use Dijkstra because it is faster. So we select based on, we have multiple correct algorithms and we kind of break the selection based on which one is fastest. Now, in the real world, Dijkstra is generally not used because you often do not care about just the fastest algorithm. So on the next slide, there are two alternatives where one is weighted A star, which is kind of a heuristic algorithm that kind of biases towards going towards the right direction as a step, and hence evaluate many fewer paths. Kind of on the extreme end, you have a greedy algorithm, which has like basically no guarantees, but can run incredibly fast. And so here there is a question of, as I said, we often do not care about the exact fastest path, but we also want to ground the algorithm to still have some kind of correctness. And so we can take both of these criteria and kind of just put them together. So on the next slide, we see that if we just take the compute time and then we add some specific error term, we can kind of get just like a simple sum quantifying the goodness of a specific algorithm. And so here we see that this error term might be very dependent on what our goals are. Like me as a user, maybe when I'm using Google Maps, I want something that is very close to optimal. So I want very small error, whereas like the Google servers likely care much more about just optimizing the compute time. And so there are different weighings for this. And this, the intuition behind this is that you're just kind of optimizing for speed. That is the main thing that you care about in solving the algorithm. And you're using this error term to ground the algorithm to like ensure that you're still getting an approximately correct solution. And so this is exactly the same thing in interpretability, where often we do not necessarily care about getting the exact explanation correct. Like neural networks can be incredibly complicated, and very likely if we have a whole explanation for the whole model, it will likely not be practical at all. So we want to make a similar trade-off where we allow some kind of error. And we can quantify that in the same way. Here, instead of using time and maybe some time penalty for like the error that you're making, you can use a notion of description length, where you see interpretability as a communication problem between sending an explanation to a specific recipient. And so here, the cost of sending that explanation is just the explanation itself, but also then the cost that of the specific correction. As you can see, that this is very Bayes inspired. You can just send the explanation, which is then the model that you have, and then the correction, like the correction of the data given the model. And so again, we can tie that back to the diagrammatic notation that we have to introduce, where you can, if you have a specific diagram, and you can kind of explain that using a syntactic interpretation. So give an explanation to all of the specific components. You're then you then have an explanation in E, and then you need to tie that back to the original semantics, to the original input-output data of your model. And so again, then you make that specific correction back to your semantics, and you can formalize it like this. And so then you clearly see that also interpretability has these two costs that we need to account for. But it doesn't just stop there, because one issue is, kind of as I said with the optimization algorithms, sometimes depending on who you are, you have a different error versus correctness, like error versus speed trade-off. And the same is true in interpretability. And so on the next slide, we see that the complexity that we have, so like the length of our explanation, can just be written as this. And on the next slide still, we see that this interpretation that we have with a specific complexity is subjective, because maybe if you're a domain expert, it might be that you can like much more easily understand me explaining a specific model to you, whereas if you're a normal person or not even human at all, it might be we might want to adapt the explanation quite significantly. But the way that we break that up here is kind of from just taking the syntactic interpretation, so understanding the meanings behind the specific components into two parts. And so the intuition here is that if you're explaining a mathematical function, there is kind of a fundamental cost. If this mathematical function is describing the interaction between multiple variables, then at least I need to explain to you what these interactions are. The mathematical function has like some base representational costs that you cannot reduce, which is just kind of conveying to you what is happening without having any notion of the variables and why they interact. And so here we decompose this explanation into this objective cost, which is kind of like the fundamental representational costs of your network or the model that you're interpreting, and into this subjective cost that can depend on the specific person that you're talking to. But this solves a very fundamental issue in interpretability, where we often do not know what it means to have an interpretable, to have a good explanation. Whereas here, in the framework of, in the compositional framework, we can kind of split the two up. And despite us still having a subjective cost, we still have a cost that just describes this like fundamental complexity. And we can further split that up into the components and the wiring, where, for example, the components can be neurons, can be layers, can be whatever that you're specifically interested in, and then the wiring is kind of the interactions in between. Cool. And just to give an example of where this can go wrong, but we'll talk more in detail if you later on. But if you just look at the normal neural network, well, you have this routing complexity. That is the wiring, where again, like this complexity might just be, oh, am I considering layers? Am I considering attention heads? Am I considering neurons? Where you might be able to trade this off. So for instance, you could have more complicated routing complexity if you're considering neurons, because you need to account for many more interactions. But maybe your components become simpler. But the problem is in normal neural networks, the kind of compositional structure is incredibly limited. And this means that if you want to minimize the description length or of this specific neural network, that you're kind of very limited. Furthermore, you have to be very, very careful that your explanation that you have doesn't become input dependent. Because for instance, for a ReLU-based network, it is very hard to understand what the symmetries are. When is a network exactly the same? And if your kind of complexity of your component depends on which inputs activated, then this might become ill-conditioned. Oh. Okay, awesome. Yes, that was all that I wanted to say about this slide.
Okay, you can still see the slides. Something changed on my monitor, but
yeah.
Okay, great. So now we essentially have a search space of explanations given by compositionality and a measure that upper bounds their description length. The question that remains is how we actually search in this space and move from one explanation to a simpler one. The main constraint here is that we cannot change the semantics that much, because that is the behavior that we are trying to understand. But we are free to change the syntax of our representation. And probably we should, because the default syntax of a model is just an implementation choice. There is no reason to assume that those specific components, those neurons, line up with interpretable units. So this is actually very much the same as refactoring your Python code. You don't actually change the function, but you try to break it down into pieces that someone else can understand. And this is also what mechanistic interpretability does already in practice. First, you decompose your model into parts, then you label those, and then you verify those labels. This translation from one syntax to another without changing semantics is what we call a syntactic refinement. And it is compressive when the new representation is shorter than the old one. So the representation complexity is going down. We are now effectively redistributing information from semantics to syntax. We take some black box that is expensive to describe and unpack it into a diagram of cheaper components. And in this way, the implicit regularities can become explicit in syntax. Because we haven't touched the input-output behavior, the explanation on the right still holds, and we can trace it back to the original implementation on the left. Now, refinement affects representation complexity, the size of the representation, because it depends only on the model. So this is an objective, measurable, and automatable thing. That's also why mechanistic interpretability has mainly focused on this first step, to find better decompositions, using tools like sparse autoencoders, transcoders, attribution graphs, and so on. But there is a catch, because we are not only only optimizing half of the true cost. As Thomas shows, there is also this interpretation complexity, the cost of aligning components with human concepts, which is much harder to quantify. A compressive refinement helps us only if the drop in representation complexity outweighs any potential rise in interpretation complexity. And we call this the parsimony criterion. The best counterexample to this is putting your model in a zip file. It will become much smaller, but it is not going to be suddenly interpretable. Because essentially, you are just moving around complexity from representation into interpretation. So it seems that smaller models are not always easier to understand. Compression only aligns with understanding under the right conditions. But we could give a sufficient one. And the intuition here is that the regularities that a model exploits to solve some task are usually the same concepts that we as humans use to understand the task. Kola et al. Call this idea, this conjecture, explanatory optimism. And they argue that all interpretability research secretly assumes this. But we can try to make this explicit, because every measure of representation complexity in the MDL framework, the minimum description length framework, comes from a specific coding distribution. And that coding distribution can be understood as a Bayesian prior. If we choose our coding distribution to encode explanatory optimism, meaning that we assign high probabilities to components that we believe are easy to understand, like sparse or low rank or hierarchical ones, then both representation and interpretation complexity will fall together. And the closer that this coding distribution actually aligns with interpretation complexity, the more reliably automated compressive refinement is going to work. If those two complexities are perfectly comonotonic, then it is, in fact, mathematically guaranteed that you will get a more interpretable decomposition in the end. All right, so before we get out of our interpretability armchair, what should we take away from this? First, if we want to automate interpretability as optimization, we need models where we can measure faithfulness and complexity. The search space is then given by refinements in the syntax, the constraints by faithfulness in the semantics, and the objective is to reduce the description length of your explanation, which under the parsimony criterion can be replaced by the proxy of representation complexity. And if you can write these three things down, you can just give this to an optimizer, in theory. This also means that interpretability stops being a binary property and it becomes a spectrum. And the existing mechanistic methods, like autoencoders or parameter decomposition and so on, they let us move around in the spectrum. And each of these methods can be studied as subclasses of compressive refinement, each with its own specific search space. A second thing is that interpretability is never absolute. If you want to claim it, we always need to specify it with respect to some chosen prior E on what concepts are interpretable. Under one prior, under the same one prior, we can easily compare explanations directly. But across priors, we need to use description length as like a standardized unit. And also, it might be helpful to reach out to cognitive science to actually discuss what priors are reasonable for humans to use, for us to use for humans. Finally, if you try to refine a model, if you try to decompose it, and you notice that description length stays high, that is also informative. It just means that there is no good explanation, or at least not in the terms that you have chosen. And in that case, it may pay off more to design models that are good at to design models that are where you can successfully do compressive refinements. So let's have a look at what those models could be. I now will stop sharing my screen, and I propose we switch to Thomas's slides.
God, that was smooth.
Super smooth.
Oh, Thomas,
You're
is this
still
your?
presenting.
Yeah. Okay, I thought. I wasn't sure.
Fingers on the buzzer. That was very smooth. Yeah.
Are you sharing now, Thomas?
Yes.
Okay. Wow. All right. Too smooth. Okay. So, well, if you remember what I said before, compressive refinement essentially needs three things. A syntax that can be rewritten, and measures of faithfulness and complexity. Sadly, for neural networks, all three of them are pretty difficult. Neural networks are compositional models because we construct them by composing neurons into layers, and layers stack on top of each other. But those components are not intelligible themselves. Their syntax consists of copy-discard string diagrams, which essentially means that there are not a lot of interesting rules to rewrite the diagrams. The upside of this is that they do get a very flexible semantics. Each box in a neural network diagram could be a universal function approximator, but only in theory. In practice, though, this means that our measures would have to work for any function at all. We would have to define the complexity for any possible function, and that is pretty difficult. So we have to resort to heuristic approximations. And this is why, on the next slide, we propose to work with tensor models, that are models whose weights interact as if they are tensor networks. They have a much richer syntax rewrite system, that of additive hypergraphs. But it comes at the cost of a more constrained semantics. For a tensor model, a single box captures only higher order interactions between inputs. And to approximate any function, we need to compose several of those boxes together. But that is also an upside, because we get to rely on the huge literature of multilinear algebra to actually decompose and measure those boxes. And as Thomas will show you now, all of the most popular deep learning architectures can actually be converted into tensor network variants.
Yeah, and the main takeaway that I want to convey during the next few minutes is that all these compositional properties and compositional understanding that we've been talking about is not just some curiosity for like theoretical smaller models, but that you can actually scale this to state-of-the-art networks using these tensor-based models. So I will talk about that first, and then talk about some decompositions on these models, and then finally talk how we can actually use this in practice. As Wart said, also actually, wait, what was it that you said? Actually do what we preach.
Practice what we preach, yeah.
Practice what we preach, exactly.
Would be great, right?
Yeah, exactly, that would be lovely. So this whole endeavor started with this very curious table from a paper. And so this is a very well-known paper by now by Noam Shazir, who is kind of a legend by now, who was studying different kinds of MLPs and introduced what is called the gated linear unit, which is like the MLP that is used in basically all modern transformers. So in this table, you should obviously know ReLU, but you could also see SWIGLU, which is the second to last one, which is generally the one almost always used. But somewhat curiously, you also have this bilinear MLP, which sure, it performs a bit worse than the SWIGLU, but it performs a lot better than the ReLU. And as Bart said, this bilinear layer is actually just a tensor. It's just a polynomial. It's incredibly simple, and so it's interesting to see that like you can scale up transformers. So I think this is on GPT-2 sized models to just use these layers without too much of a cost. And so I'm not encouraging you to specifically read this paper, but this paper has by far the best line found in any paper at all, which is we offer no explanation as to why these architectures seem to work. We attribute their success as all else to divine benevolence, which is absolutely the best way to end your paper. Although I'm not sure how much you will get accepted to conferences, but anyway. So yeah, as I'm saying, this bilinear MLP or this bilinear layer is actually super similar to what you might know. So for instance, when you go from a ReLU to a bilinear layer, well, what you're actually doing instead of your ReLU kind of being this gate that like multiplies your outputs of some matrix by 0 or 1, you multiply by just some other matrix, such that you have some like dynamic kind of dynamic activation function. And so if you're coming from a SWIGLU, the only thing that you're doing is removing the nonlinearity, removing this swish function. The swish function itself being x times sigmoid x. And so the thing you may ask, like, oh, but the middle part is just matrices and some element-wise multiplications. Well, it represents a polynomial. The element-wise multiplication gives it its nonlinearity, but since it's just an element-wise multiplication, it can be very easily studied. As I've been alluding to, this represents just polynomial interactions. It's very well describable. And I will be using some diagrams. I do not expect you to like understand everything that is going on. These are more for visual reference. But for attention, you can also do the same thing. So we have our ubiquitous softmax attention. But on the right side, you may also be familiar with linear attention alternatives. I am talking about the Mamba, more recently the Delta Nets, even Hyena. There's so many variants of them that kind of try to use the linearity in some linear algebra tricks to avoid the quadratic complexity of attention. And generally, you can also scale them to state-of-the-art models. On the left side, you could also use polynomial attention in itself to kind of increase your expressivity, yet still at the cost of quadratic cost. And so we did some experiments where, well, we just took, like, despite us not inventing these components, we just put them together, which is something that hasn't been done too many times before. But what we see is if we have our baseline, which is just like the normal kind of transformer model, well, any of these replacements that we do with these components, it's not necessarily noise, but like there is not too much variation. Like there's not this, let's call it like the interpretability trade-off that we often talk about. And even for reasons that I wouldn't get into for chess, using these compositional variants, these tensor networks is actually like quite significantly better. And so again, and so this is just on 40 million parameters. But we've shown that this scales up to 500 million parameters, and likely there's not really a limit to this because again we're kind of using very standard components. And this I find this very interesting because you can see this tensor as just a polynomial, and if you're training GPT-2 sized models, here 40 million parameters, you can train a polynomial to speak coherent English, which is a very funny concept to me. And so then the question is, well, okay, we have these models that should be analyzable in practice. They should be compositional. Okay, how do we actually decompose them? So again, I will be using some mathematical notation. It's not too important if you understand the diagrams. As Wart said, there's a lot of math like going into this. I just want to show the intuition, where at least working with matrices, I think everyone loves matrices. They're super nice to work with. And so there are some elementary operations that you can compute on a matrix, such as a norm of a matrix, where, maybe if you have a matrix and then a submatrix, you can compute what the fraction of that submatrix is within the bigger matrix, kind of finds how much of the original matrix that you're explaining. You can do that using norms. The same like a similar thing is computing gram matrices, which is kind of like the building block of SVDs and other linear decompositions. And so you can just write this as a similar diagram. Now, the interesting part here is that we can do the same thing for tensors. We can compute tensor norms. And if you look on the right, you actually see the same structure as your bilinear layer, where you have these three matrices that have an element-wise product in the middle, and you can just compute their norm. Furthermore, you can even compute their eigendecomposition. You can compute SVD on them, because they are closed algebraically. You can basically compute whatever that you want on these tensors, and more interestingly of all, you can compute that efficiently. Not just for these small single layer models, but as you stack these models, you just get more complicated tensors. But it seems that smart mathematicians have figured out algorithms that just work perfectly on these deeper models that constitute tensors. And again, the intuition is that you just have this polynomial, and since your polynomial is fully weight determined, you know just by looking at the kind of the weights of your model what the factors are of your polynomial and which specific variables interact how, that you can decompose this without losing any guarantees of equivalence. And so one experiment is then, okay, sure, that all sounds nice in theory. So we take an 8-layer MLP that is trained on emnist, which is a slightly more complicated version of emnist that also has written characters, so the whole alphabet instead of just digits. And so yeah, we have this specific model, and then what could be done to let's say compress that model, or what some people have done to interpret that model, is compute SVD on the specific matrices in that deep model. And then you could imagine, okay, sure, if I am looking at n components of that matrix, how much of my model am I explaining? And so here what we do is we do SVD on all the matrices, and the local baseline is precisely this. Then we throw away the smaller singular vectors or singular values, and we see that actually the accuracy very quickly degrades. So just by looking locally and trying to compress locally, we're not getting very far. If we cannot concisely transmit this. Whereas if we use this global algorithm that I had been talking about, where we can just compute kind of the SVD of the whole polynomial and use all that global information, we see that we can actually just throw away half of the dimensions without hurting accuracy at all. And you can see that the curve is quite a lot steeper, down to kind of 80%, which is your requirement to just pass along the amount of information for the predicted output classes. So we can see that taking this these tensor networks just give us so much more structure to use algebraically to find better decompositions. Okay, so we've now discussed rank decomposition. Okay, as Wart said, maybe you do not think that is useful prior to have to interpret a model because you still kind of have dense interactions. Okay, but you could also just do a sparse decomposition. So this is slightly more involved. Sparse decomposition is known to be a bit harder, but you can still have the same guarantees. And following some very well-known papers, like for example the lottery ticket hypothesis, it shows that you can actually throw away so many of your weights while retaining accuracy. And so here we can throw away a bunch of our weights, but to keep the algebraic structure in our tensors, because we can have multiple specific matrix or tensor factorizations that yield the same model. It's kind of like a Boolean formula that you like factor in different ways. And so here we can do the same thing, and we see that, oh, once we try to describe this model, okay, the original model here using this prior has 5 million bits. As we sparsify more and more, at first there is a small peak, which is kind of an artifact of how we're transmitting the model. But near the end, you have kind of decimated the transmission costs, because your whole model is just a very, very sparse circuit. So, okay, we've seen that that there are these decompositions that you can do that in theory reduce the description length of your model, and that then again, based on if you believe any of what we said, would also yield more interpretable, would yield nicer explanations. And this seems to be the case in practice. So you can take this small model, like a small image model, and as I've been saying, all the analyses that we've been doing are purely on the weights. So we don't even know what, like, we are just given basically a bunch of numbers. We do SVD, and then we project that onto the input space. And then we see like, oh, okay, if we look at a specific output class of this model, what does it predict? Or like, what does it activate strongly on? And so again, these are not attributions. We have not used any inputs. This is just like using the weights and kind of looking at the eigenvectors of the model. And we see that that corresponds to like super sensible things. And even more importantly, what you can do is the kind of noise that you see here, you can like cut that out and then use that as adversarial examples. So you can like adversarially inject that noise into other digits and show that like the noise that you see at the edges is kind of the model overfitting, which is super interesting. Something else that you could do is, which is not necessarily in interpretability, but given, again, these algebraic properties, is look at the training process of a model, where we change the training distribution and the model changes accordingly. And if we look at CKA, which is basically a tool to compare activations of models, we can kind of track what is going on. But if we use these tensor methods, where we like kind of from the weights compare using the compositional structure, how the mechanisms and like what the model computes, how that changes, you can see that it's much cleaner. So it doesn't have like any of the activation artifacts, because you're using like the whole algebraic structure of the model. Yeah, and again, like I'm kind of just giving a whirlwind tour because there's so many things that you can do. But something else that has been of interest lately is neural geometry. So it's like if you look at the activations of models, you can generally find that these span like they have super interesting shapes. And so here again, using compositionality, you can generally get quite nice results, because most techniques, as I've said, take activations and try to sparsely decompose them. The issue is that this kind of makes assumptions about the activations that might not always be correct, and then the model is like kind of falling into slight degeneracies trying to optimize that sparsity. Whereas it seems that if you optimize towards this more like sparse composition, that you get much cleaner shapes, I'd say, of like how the representations are exactly formed. This, by the way, is in a protein model, which they have the coolest shapes and like thinking have really interesting activations to study. And kind of as a last example here, we've also used this like in like actual practice, not just academic practice, where we use this idea of a bilinear layer and turn that into what we call a covariance probe, where this is just kind of this compositional probe over a sequence, where here the sequence that we considered was embeddings over DNA. And so it turns out that if you use this kind of like interpretability first technique, that you are able to get the state of the art in disease prediction based on just the sequence of DNA. And this is like state of the art with like comparing to actual biological methods that have been studied for decades. If you just look at like a competent model. And yeah, this was featured in Time magazine, interestingly enough. And what you can then do is, like, because you're just using interpretability and you have this compositional system, you can then not only predict when specific DNA could contain a disease, but you can decompose that into the constituent factors, which we then used to generate explanations of why the model thinks that specific DNA contains disease, which we then turned into text that clinicians can actually use. And I think this is a lovely example of interpretability that is like kind of made possible through this compositional approach, where you have these like strong guarantees that we can decompose what we're explaining. And so, given all of these examples, the main point that I now want to make is that yes, if you carefully pick your framework, you carefully have compositional explanations, ensure that your explanations kind of make human sense, where the sum of the parts constitute the models and vice versa, and then compress these explanations, you get interpretability or interpretable models. And with that said, I want to thank you all for your attention. And if you have any questions, please ask. These, well, I mean, Wert and I, you know, these are our supervisors. And if you want to go to our lovely website, please, oh, the lights just went out. If you want to go to our lovely website, please scan the QR code. Thank you.
Amazing. Thank you so much, guys. It was super interesting. We have probably time for maybe 1 or 2 questions. Get to you raise your hand or clap. Oh. Cool. So does anyone have any questions? If you do, just unmute yourself.
Well,
yeah,
I do. Thank you for the presentation. And well, I have a few, but I'll start with this. So, if I understand correctly, you're saying that you can consider a model where the input and output semantics is fixed, and the internal structure can be rearranged. Like, part of the framework is rearranging the internal structure to minimize the complexity while keeping the input-output semantics fixed. The question is, like, while you keep the input-output semantics fixed, the internal semantics of the model, when you rearrange the syntax, may differ, right? You may have a model that 2 different models with the same input and output semantics, with different with syntax that are compatible, so you can write the syntax of the one into the other, but the internal semantics is completely different. So, for instance, the internal concepts are different. How can this be how can this framework guarantee that the internal concepts are the same when you change this internal syntax?
Okay.
Mm-hmm.
So we do not assure that at all, right? So, I mean, I like to think about search algorithms too. Like, you might have one algorithm that just sorting algorithms. You might have a bubble sort, and of course I cannot remember another sorting algorithm. Quicksort, right? Both of them, like, if you explain one algorithm to a person or the other, you explain it using different concepts, right? So pairwise comparisons versus like the splitting action that's going on. So I don't think that for our notion of interpretability, this is a requirement. I could imagine that you do want to have models with shared internal concepts, but then this is something beyond the basic interpretability framework, maybe.
Yeah, and I think given the description length, what you could imagine is that you have a description length that isn't targeted at explaining the model to a human, but explaining the model to kind of another model or something, that you kind of have a description length of how your internal semantics are changing, where, for instance, you could imagine, like, what to use the analogy of sorting algorithms, I generally like to think about like Boolean expressions, where you have this like very complicated expression, and they have different factorizations, where you have different intermediate variables. Well, within the compositional framework, we just kind of ensure that, given a variable, you could technically write another variable as also like as a Boolean expression, and you can understand how they kind of change. But that expression might be arbitrarily complex. You might have some kind of cost function that says, only change the representations if like reduce the complexity if like it also outbalances the kind of internal changes that you're making, if that makes sense.
Just to ask a clarification about this, but does this mean that basically there might be multiple explanations, valid explanations, with a different internal semantics for the same original model, right? Okay.
Yes. Yeah.
Depending on the user, depending on the algorithm that you use to compress the model.
Yes. I mean, as we said, like you might want to explain something in terms of pseudocode or in terms of a causal model, and then naturally, like the semantics in which you have to translate will be different. But syntactic refinement stays within the same semantic category always.
Thank you.
Okay. I have one tiny question. I hope if I have time for it, that's okay. Unless you guys have to go, please let me know and cut me off. No. Okay, so it is more on the. If you can go back to the results on the MNIST one. Okay. That's perfect. So just to clarify this, so did you have evidence, or is there like any? Have you experienced or seen it happening where I can't remember exactly how these were generated, but where you did generate this was only possible because of the compression and would not have been possible before the compression. Is that what you observed, or is it something that it's easier with the compression, but still would have been possible without it?
Mm-hmm. So this is kind of doing the SVD on the model and then looking at the highest singular value and then projecting that out. So it's like the kind of inputs that would maximally activate the model for a specific output class. So it's in some sense not like leveraging the compression. It's just like looking at what is the most important thing in the model, and then.
Let's treat it as if it is a linear model, right?
Yeah.
Let's forget about all the other stuff.
You have a way that you can decompose it into the.
Let's say you do a SVD on this, then you get an eigenspectrum, eigendimensions, ordered by importance, and you could think about truncating it. So when we show you this this picture of a tree, this is actually an explanation of the model when truncated to a single dimension.
Yeah.
So we are still doing compression. We have other figures also, not in our forthcoming work, but in our already published work, where like you use 5 dimensions for one specific class, and then you see these are like different tree patterns, and then you are essentially compressing to 5 dimensions.
Okay, I see that. Now, have you happened to cross around some example where you couldn't see before? So, for example, I could generate something. Obviously, it's a very different approach, but I could generate something very similar to this using something like activation maximization or some other like classic post-hoc end-to-end kind of approach. You can see. Let me look at things that actually activate something. And you'll probably get something very similar instead. Have you spotted an example where this is not the case, where you get something just because of the compression and the fact that you can, as you said, you can pretty much run SVD on the entire network almost? in an equivalent manner.
So two things here. The first is, so as Wart said, you can here, like, okay, you get one image and like this is the nicest one, but if you look at like the next kind of eigenvectors, they, for example, correspond to like a specific part of the four. So actually, like the three biggest eigenvectors for the four, one is like kind of, the first is archetypal, and the next ones are like this. I'm not sure if you can see my cursor. Yeah. This is like an edge detector, then such an edge detector. Like really, it's kind of exactly what you want to decompose into. So this, first of all, is kind of hard with activation maximization to like really decompose into parts. This is just like one example. The second is, here you have a guarantee that if you sum all of these components together and you understand all of them, that is the whole model.
Yeah.
And you can even compute how much of the whole model that you're understanding. Now here you're looking at one, so like you're understanding like 5 to 10% of the model. It's not that much, but yeah. So it's more about like the correctness rather than the actual image that you get. And furthermore, generally here you actually get cleaner images than in activation maximization.
Yeah, I can imagine. Activation maximization is a bit of a dark magic to get it working properly.
Yeah.
one also, I think, very cool results, which was obtained by a master student of mine, Antoine Dehéran. He basically applied this. So this, what you're seeing here, is just a feed-forward MLP, 8 layers or so. He applied this to a convolutional neural network, and then the patterns that you are outputting, depending on the specific kernel sizes that you use and so on, you very clearly see that your eigendecomposition is showing you exactly those line segments that the model is looking for, and you know mathematically that they are just summed together in the end. So that's very nice to see. I'm trying to get the picture, but I'm afraid it will take too much time.
Yes, that's pretty cool. Yeah, sorry, just literally one quick follow-up. I found it super inspiring because I wonder if you already have the composition, and then you could. There's ways that you can interact with it. For example, you detect one of these directions corresponds to some sort of weird style of force. You can actually then verify if that's the case by doing interventions, right? Like you can drop that dimension when you reconstruct the model, or like the composition, just drop it, and then see if the only thing that stops being predicted correctly are those forces. Have you experimented with like doing these sort of interventions on the composition level and then sort of reconstructing it?
So that intervention we haven't done, but so one intervention that we did is like use the noise patterns from like the sides, so like parts that really do not correspond to digits, and then inject that noise into other input samples, and then actually you see that it really confuses the model.
I see.
And one thing that is also quite interesting there is, so when you look at the eigenspectrum of such a decomposition, it is very steep. So this essentially means that for any particular class, an 8-layer MLP is just memorizing whole digits. It's not learning line segments at all. But then when you apply this, for example, to a convolutional neural network, you see that your eigenspectrum flattens out, meaning that all of those very small patterns actually contribute, like it is actually just composing those small convolutional patterns and choosing like, I want this curve here on the image, this curve here, and so on and so on. But the one asterisk for this is, of course, this is if we believe that low rank representations are interpretable to humans. If you try this on a giant transformer, which is not based on images, like it's not going to be that nice to look at.
Yeah, this is just like because the data sets that we're studying are kind of simple, and you can decompose that data set into like a sum of nice pictures.
Yeah,
like this obviously doesn't always work.
Like imagine there might be some domain where the spectra sort of corresponds to a measure of compositionality of the model, right? But I don't know if that would apply for very large.
Well, this is not necessarily like like this is a trivial form of composition, right? You're just summing, so you're kind of flattening, so you're actually like kind of throwing away the composition in a sense, right? But it's just the fact that you have this compositional structure that you can flatten closed form. But ideally, you would want to keep the compositionality, yet you then have like more complicated interactions that are not just like sums between these images.
Yeah.
Are hard to think about.
Yeah. One thing. So I mean,
I do need to
it's-
head off though.
Okay.
So yeah.
Thank you so much,
Right, Thomas. See you around. So one thing I just wanted to mention was that so it is nice that with these tensor network models, like we can just use multilinear algebra. It's very nice. And this makes it easier to measure faithfulness, easier to measure complexity. We know a lot more about rewrite rules, but there is still one fourth aspect which I didn't mention yet, and that is that we actually need to believe that the units of which such a tensor model is built up are more aligned to something that humans can understand. And this is where it actually comes back a bit to neurosymbolic AI, because we know that probabilistic circuits, declarative programs, symbolic programs, they can be compiled into tensor networks. So it is very nice to have this one mathematical object that it seems we can use both for to build models that are intrinsically interpretable, and to decompose models that are that may become more interpretable. So this is why I would believe that like this is a very nice, like on the Pareto frontier of all possible models, this is a very nice point to be at.
That's very interesting. Thanks.
Super interesting. Yeah, I do have to go as well. But yeah, thank you so much, Bart. Really, really appreciate it. It's been fantastic.
Thank you for the invitation.
Yeah, and do send us the paper, the follow-up one when it's done, because I'll be curious.
Yes, yeah, we will. We have been working on that one for a while now.
If you want, you can present it in another time at the same.
Great.
Absolutely.
Yeah, absolutely.
Alright.
And I just also wanted to mention, I have seen your papers, obviously, about symmetry-based formalizations. And I'm a big fan of those. I've been thinking quite a lot about how they overlap, specifically with your standard interpretable model approach, because it is very much aligned with what we are saying, right? We are just, I guess the biggest difference is like, well, you need some set of symmetries. Where should we get them? I would argue you need to derive them from compositionality and minimum description length. But I would love to talk more about that to you maybe some other time.
We can reach out by email. Thanks.
Alrighty.
Thank you, guys.
Thank you so much, everyone.
See you next week. Bye-bye.
Bye. Yep. Thanks a lot. Bye-bye.
Thanks.
All right, thank you.